Okay, I think it's live now, so we can wait for a short time until the bell rings and then we can start. Okay, I think I heard the bell. Okay, good. I assume everybody can hear me. That's great. I can see people. That's also good. So let's get started. As always, with Fridays, we have fewer people in the room. And I wish I could be in the room also, but I'm still a bit sick, as you can tell from my voice. And I hope to get out of this mode next week and see you all in person, which is much better, frankly, on my end, and perhaps better on your end also. But we have another exciting topic to cover today. Actually, we're going to continue what we have started yesterday, which is we raised the abstraction level yesterday to instruction set architectures to the hardware-software interface. And today, we're going to continue with this raised abstraction level and see a lot of interesting things in instruction set architecture design. In this lecture, normally in lecture 10, we cover instruction set architectures and assembly programming. What we will do is I will cover instruction set architectures and we'll assign assembly programming as a lecture you can watch on your own. You will need that for your labs, especially, and it's good for you to learn assembly programming, but it's relatively easy since you know the basics of programming by now based on the courses you've taken. Assembly programming is not that much different, let's say, except you do it at a much lower abstraction level. Okay, so we will announce how you can watch that lecture later on. But today our focus will be on instruction set architectures and trade-offs. So initially I will cover some high-level trade-offs related to instruction set architectures because these make a big difference actually in how you can program and how you can design a compiler, how you can design the microarchitecture. And then we will go into different instructions and different addressing modes, especially things we did not cover yesterday. Okay, just to jog your memory, you know that there are some assignments that you can complete for extra credits, which hopefully is great. And this was our agenda for today and next few lectures. Today, we're going to finish instruction set architectures and you will do the assembly programming on your own. And then next week, we're going to start microarchitecture, which is a fascinating area where we will see how we can actually optimize the design of the microarchitecture to maximize performance and efficiency. Okay, so what will we learn today? Essentially, we covered the von Neumann model yesterday, basic elements of a computer. I'll remind you quickly what the basic principles are. And we started learning about instruction set architectures, of von Neumann instruction set architectures, and we looked at these 3 different types of instructions. Today, we're going to go deeper into addressing modes, for example, and some trade-offs in instruction set architectures and how they affect the programmer and the compiler and the hardware designer. So hopefully it'll be fun. And readings, remember, we're following Pat and Patel chapters 4, 5, and 6, but you can also do the readings in Harris and Harris. Again, you don't have to do the readings if everything is perfectly clear in the lectures. So before I jump into new material, let's quickly review the von Neumann model. This is basically the pictorial view of the von Neumann model. It consists of 5 components: memory, processing unit, control unit, and input and output. And we discussed each of them yesterday. We focused a lot on the control unit. Yes.
We disconnected from Zoom for some reason. We are rejoining.
Okay, you're disconnected. I see.
Yeah, sorry.
Okay, I will wait then.
Yeah, thank you.
I think the live stream people are okay, but why don't you rejoin? Is it good now, or is it still problematic?
We lost the Ethernet connection here. We are going to connect to the Wi-Fi now.
Okay, that's not good.
Yeah, I don't know why.
Okay, in the meantime, I'll handle some questions that I saw on YouTube just now, actually. Somebody asked in processing unit, what is that temp? We discussed that yesterday. Remember that you need some fast temporary storage called the register file. That's very close to the processing unit, ALUs, functional units. And that's what that temp is. And then there's another question. What is the relation between the instruction types and Turing completeness? Turing completeness is basically whether your machine satisfies the properties of a Turing machine, right? And instruction types can certainly enable you to become Turing complete. So there is some relation, certainly, if you have instructions that can enable you to operate like a Turing machine, then you become Turing complete. So you need to have instructions that enable you to be Turing complete based on the definition of the Turing machine that Turing proposed more than 70 years ago. So there is some relation, certainly, but that's not really the subject of this course. Every ISA we discuss here is Turing complete, and it doesn't really take much to be Turing complete in existing systems, I should say. Okay, looks like you're back in the room. Can people hear me? Okay, good. Maybe you can change the orientation of the camera a little bit also, so that we can see. I can see people better. Now I'm looking at the top of the room. Okay, that's better. Okay, so I answered some questions on YouTube in the meantime. If you were wondering about it, you can watch the live stream later on. But basically, we covered the von Neumann model yesterday. We covered all of these different 5 components, and hopefully you know them very well. And we covered 2 key principles, 2 key properties of the von Neumann model that is critical for essentially programming von Neumann systems. So stored program computer instructions and data are in memory, unified in a linear memory array. And the interpretation of a stored value as instruction or data depends on the control signals. And we actually covered that in a lot of detail. And the second property is sequential instruction processing. Basically, one instruction is processed at a time, and then you move to the next instruction in sequence using an instruction pointer program counter. And these 2 properties are the hallmark of the von Neumann model. And these have been extremely successful in enabling a vast majority of people in the world to program relatively complicated general purpose machines, basically, because these are very easy to reason about from a programmer's perspective. Okay, and then we also covered the notion of programmer visible or architectural state, and we talked about 3 major things that are part of the architectural state. These are things the programmer can modify, and there's a contract between the hardware and the programmer, which is the ISA, that specifies how these things can be modified using instructions. And instructions specify how to transform this programmer visible state to some next state, let's say, by doing updates based on each instruction. Okay, so hopefully this is clear also. As we also discussed, there's a microarchitectural state. There's state underneath that's not visible to the programmer, and we'll cover that a lot in future lectures. But a programmer cannot modify the microarchitectural state directly. They can modify the programmer visible state, memory registers and program counter, general purpose registers and special purpose registers directly using instructions. And we covered a von Neumann machine, which is LC3, and this is a data path and control logic, abbreviated, let's say, because it doesn't go into every single detail in terms of a gate level. But we covered essentially all the components of that you're seeing over here, and we showed examples of how instructions get executed on this machine as well. So now we actually have a very good idea of how a machine is built, even though we didn't build it from the ground up. We'll do that actually in the next lectures next week. We're going to build a machine from the ground up. We didn't do that here. We kind of assumed that, okay, you have this machine somebody built. Here are some instructions and how they execute on this machine that somebody built. And that's a very good exercise also, because now you know actually how the instructions relate to the underlying microarchitecture, which is what you're looking at right now. And again, there's no magic. Everything that we have seen in this picture is based on what we have covered in the past, right? You see combination logic, you see sequential logic, you see clock, you see multiplexers, you see ALUs, you see gating signals, which are actually tri-state buffers, you see register files. So we've actually covered almost all components of it, except we didn't build it from the ground up. So that's what we will do next week. But before we get into next week, what we will do today, basically, we also covered the instruction processing cycle yesterday, not to be confused with the clock cycle. This is basically the stages that an instruction needs to go through so that it can be executed on a one Neumann machine. And you can see that there are 6 stages. This could happen in a single clock cycle, as we will see early next week. This could happen in multiple clock cycles, as we will see later next week. But basically, every instruction needs to go through these. Not every instruction requires every one of these stages, basically, as we also discussed. But we will see how to optimize things next week. And this is where we ended kind of yesterday. And I want to spend some time before I move on to contents of today's lecture. Remember, we're talking about a finite state machine. So let me go back here. There's a finite state machine over here that really controls the execution of everything that happens in the computer. And this is the finite state machine. This is a state diagram, basically, of the finite state machine. State 1 is a fetch state, as you can see. State 2 is also a fetch state. State 3 is also a fetch state. Basically, in state 1, the finite state machine generates control signals such that it asserts gate PC and LDMAR signals. We've actually seen this. If you go back to the previous picture over here, you have the program counter. Program counter gets gated and loaded into the MAR. Remember, we said that's how fetch happens. That's basically the first stage of the fetch. At the end of the clock cycle, program counter is in the memory address register, so you can access memory with that in the second state. So that you can get the instruction pointed to by the program counter. Also in the fetch state, PC gets incremented so that you can move on to the next instruction at the end of the execution of this instruction. Remember, this is an optimization. PC does not have to get incremented immediately, but for some other instructions, when they calculate some addresses, they require an incremented PC, as we will see in the specification of the ISA. So basically, the designer, microarchitectural designer, has some freedom as to when to increment the program counter. Keep that in mind. But to fetch then the next state is basically the memory accesses its own addresses using the memory address register and gets the data in that location, which is pointed to by the program counter, which we loaded into the memory address register. And then the memory data register now contains the instruction encoding. And then in the third state, memory data register gets loaded with the instruction. And we need to set the appropriate control signals in the machine to enable this. And we talked about that again. And with the appropriate control signals, gate MDR and LDIR. So let me go back quickly. Again, I'm skipping slides, but MDR at the end of the second state contains the instruction encoding. We gate it onto the bus using the signal, enabling the signal. And then the data gets into the IR instruction register. We latch it by ensuring that we set load IR to 1, meaning IR should be write enabled. And write enable takes effect at the end of the clock cycle, at the beginning of the next clock cycle, as we discussed in finite state machines very clearly. Right? So this is a finite state machine, basically, which we had built examples of in prior lectures. And then the second, state 4 is decoding. In the decode state, that's finite state machine basically decodes the instruction. Remember, we have 4 bits of opcode, meaning we have 16 potential opcodes. We have 4 to 16 decoder. And based on the bit pattern that's in the opcode, you jump into a separate state. So there are 16 possible next states over here. One of them goes to here, for example. If it's a jump encoding, then you go into that first state. So this is the first state after decoding for the jump instruction. Okay, that's state 5. There's some number for the state, but it's not provided in here. In the next slide, I will show you the full state diagram. And then, of course, we know that we're executing jump instruction. The finite state machine is actually going through states for executing the jump instruction. And there's one state over here, state 63, where the register, remember the jump instruction takes a register, source register 1, and writes the value of it into the program counter. And that happens in this state part, in this particular state over here. Register contents get loaded into the program counter. And for that to happen, you need to assert the appropriate control signals that make that happen. And if you go back, I'm going back and forth between the state diagram and the microarchitecture picture, but that's how things work, actually. You need to do that. Basically, the SR1 value over here gets written through the program counter mux into the PC. So you need to enable load PC signal, and you need to select the right control signal that selects this SR1 and passes it through the mux in that particular state. So every state enables different control signals in accordance with how the state should execute, basically. And this is a very fundamental principle. That's how you control the machine. The finite state machine generates control signals in every state specific to how that state should behave. Okay. And at the end, this is jump has finished. So you go to state 1, basically. And state 1 fetches the next instruction because we incremented the PC, right? So that's how things work, basically. This is our instruction cycle. This is how we control the instruction cycle using a finite state machine. And this is just part of the finite state machine. The full diagram is in Appendix C. And this is the full diagram for LC3B you can find on your course website. And also in your book, you can find LC3. But these are very similar state diagrams. One is byte addressable, one is not byte addressable. And there's some change in the instruction set architecture. So this is a very simple machine. So the state diagram you can see is very small, right? It's less than 64 state, actually. You can encode each state with 6 bits. But in a real machine, for example, you may have millions of states. In a real machine, the finite state machine may look actually unwieldy, very difficult to draw on a piece of paper. And that's true in existing machines, actually. We have millions of states, if not billions potentially, right? Depending on the amount of processors and amount of accelerators that you have in existing systems. So the state space has exploded in existing systems today. But that's why we're studying simple systems so that we can understand the state space. So that was our von Neumann machine. I took some time to explain you the state diagram because I think it's important. And we're going to talk more about it next week, except we're going to assume a very simple finite state machine to begin with when we construct our basic microarchitecture next week. And then we're going to build up to multi-cycle, bigger state machines, and then pipeline processors, and then out of order execution processors, which are very close to how things happen today in a general purpose processor. Okay, and then we actually showed pictures of von Neumann machines. This was my joke about PowerPoint, but essentially all general purpose processors today are von Neumann machines, and they operate based on the same principles. And this is just to jog your memory again. And this is where we stopped yesterday. We were going to go deeper into LC3 and MIPS instruction set architectures. Along the course, we're going to cover some trade-offs. Some I believe are quite fundamental and exciting trade-offs. And again, just to remind you, instruction sets are there for general purpose processors, right? Keep this in mind. If you have an FPGA, for example, you don't really have an instruction set. You basically map your data flow graph, as we will see later on, to an FPGA. But on top of that, you can implement an instruction set that is based on that data flow graph. Okay, keep that in mind. You're going to actually use the FPGAs to build an instruction set on an FPGA in your labs, but that's not the only usage. You can actually use an FPGA as an accelerator where a data flow graph of a program just gets executed. If you didn't understand that, we will get back to data flow in the next few lectures. That's a completely different way of thinking about computing. But I wanted to first start with the von Neumann model, which is general purpose and the dominant general purpose way of thinking about how to design computers. So we're still in the general purpose domain, basically. So instruction set, as we discussed yesterday, defines opcodes, data types, and addressing modes, and many, many other things, as we will discuss. And we covered add and load register as our first examples in LC3, and we covered similar instruction in MIPS as well. So this was add in LC3, if you remember, register to register, and this is the encoding, it's 16 bits. And this was LDR in LC3, this is the encoding again in 16 bits. So these use two different types of addressing modes. One uses the register mode, which we will see again. Basically, it adds 2 registers and stores the result into another register. And the load register uses the base plus offset mode. Basically, it takes a base register, adds to it an offset, an immediate value that's part of the instruction, as you can see, and computes the address that way. So addressing mode specifies how you compute the address in an instruction. And we're going to see more addressing modes today. But before we go into it, let's basically define the instruction set architecture again. As I said, this is what the programmer assumes what the hardware provides. It's really an interface. It's really a contract between the software commands and what the hardware carries out. So it really sits in between the high-level software, as you can see over here, and the low-level hardware. So it's this yellow thing over here called the ISA. It has a special function bridging the gap between software and hardware. And as a result, it needs to specify things extremely precisely and clearly, right? You cannot make a mistake over here. Otherwise, the programmer may assume one thing and the hardware may implement something else. As a result, you may not be able to do things that you want at the software level by using the interface that's provided in the ISA. So there has to be this contract that's obeyed by both parties, if you will. So the ISA, as we discussed, specifies the memory organization. We said address space, addressability, and we looked at different ways of addressability, like word addressable. LC3 was word addressable. MIPS is byte addressable, as you can see. Address spaces are also different. Today's address spaces are actually much larger. In lecture 25, we will cover virtual memory when we talk about address spaces on the order of, let's say, 2 to the 64, for example. So it's going to be very interesting. But ISA specifies this. ISA also specifies the register set. These are fast temporary registers. And you can see LC3 has a smaller number of registers. MIPS has a larger number of registers. It's a more real system. And we also discussed the historical context. Initially, x86, which was designed in 1970s, early 1970s, had 8 registers only. But over time, people said, oh, this is not enough for the software to express the temporary variables that it's dealing with at a given point in time. So people have increased the number of registers to 32 in x86 today, maybe even larger today, actually. I haven't studied the very, very latest version of x86. So we have many, many more registers. Later, we will see GPUs. GPUs actually have a much larger register set because they're operating on many, many, many data elements at the same time. Okay, and the instruction set essentially specifies opcodes, data types, and addressing modes, and more, and the length and format of instructions, as we have seen. Now we're going to focus a little bit more on the opcodes, data types, and addressing modes, and some trade-offs associated with them. Okay, so let's start with opcodes. These are another way of saying instructions, but opcode is a specific part of an instruction that specifies what the instruction does, right? We talked about opcodes and operands. Opcode is what the instruction does. Operand is what the instruction, who the instruction does, what it does to, essentially. So let's talk about opcodes. So opcode is actually, there may be many opcodes that you can define, right? If you think about an interface, you can say, okay, I want to have opcodes that can do not, and, or, XOR, and then I want to have multiply, I want to have divide, I want to have square root, I want to have load, store, and then maybe you can become more fancy, right? You can say, oh, I do a lot of matrix multiplications. Why don't I have a matrix multiplication as an opcode, right? Now you can imagine that there's a huge trade-off space over here. Does it really make sense to have a matrix multiplication as an opcode in your system? How often does your system execute matrix multiplications, for example? That could be one consideration for this. So basically, there's no end to this, if you will. You can specify if, a doubly linked list insert operation as an opcode potentially, right? So it's based on the imagination of the person who is designing the interface, and also what happens in the software, right? Ideally, you would like to map the software constructs nicely to the opcodes. Okay, so let me talk about some examples. For example, HP precision architecture, this is actually relatively old, in the 1990s, there was an instruction for floating point multiply and accumulate. So this is multiply plus C, A times B plus C. This multiply and accumulate. A lot of instructions and architectures at the time did not have this instruction. These folks were actually very forward-looking, in my opinion. They added this instruction because they said, oh, this is very good for matrix multiplication. This is a primitive for matrix multiplication. When we do matrix multiplication, we do multiply and accumulate, and we do many of them. And we string together many of them. And they said, if we had a multiply and accumulate instruction that does multiply plus add, then we could actually make it easier for the compiler to map the high-level matrix multiplication code into this, and scientific code also into this. And this is actually quite reasonable design choice. But another design choice, basically, I don't have this. This is more sophisticated than an add and also a multiply, right? It combines both. So this is a choice that's made by the ISA designer in the end. Okay, x86 ISA has some sophisticated instructions called multimedia extensions. Today, actually, all ISAs have it, but x86 is one of the first ones. It was the first one actually to introduce it in the general purpose space. Later, this is called SSE or AVX, Advanced Vector Extensions. Basically, these are instructions that can operate on multiple data elements at the same time. You say you specify an add. Add happens on 8 data elements concurrently at the same time. It's very similar to what we will call single instruction, multiple data. But this is a complex instruction. This is not simple. You're not specifying one single add. You're actually specifying multiple adds concurrently. Okay, so this is another example of a, let's say, more sophisticated opcode than what we have seen so far. Okay, VAX ISA, which was one of the most sophisticated and most complicated ISAs in the world. This is actually historical. This was actually a dominant ISA before x86 in the 1980s and late 1990s. It had an opcode to save all information of one program prior to switching to another program. Basically, this is an instruction called save context. It was saving architectural state of one program to memory so that you can switch to another program. So it also had the load context instruction. It would take the context, architectural state of another program and load it into the machine. So you can see that this one opcode can actually do a lot of powerful work. Even though it's a single instruction, it can potentially do hundreds of thousands of operations, right? To save things into memory and to load things into memory from memory as well. Now you can see that there are many, many different kinds of opcodes than what we have seen so far. And there are a lot of trade-offs involved. Clearly, hardware becomes more complex. If you have an opcode that specifies a lot of work, your hardware becomes more complex, right? For example, if you have matrix multiplication, now your hardware needs to take one single instruction and multiply two matrices together based on the specification of the instruction and store the result somewhere as specified by the instruction. So hardware complexity becomes higher. And if you have many opcodes that are complex like this, hardware complexity becomes higher and higher and higher, right? You can have multi-dimensional arrays. You can basically have multi-dimensional array indexing, for example, so that you can better support scientific programs. And that makes the hardware complexity higher. But software complexity becomes easier in the sense that at the software level, at the high level software, you have a matrix multiplication operation, and the programmer can specify that. And this can be easily mapped to an opcode. It's a single opcode in the machine, right? Compiler doesn't need to do a lot of work to map it, meaning that compiler doesn't need to map it to a level where it needs to go through load, store, add, multiply, calculate the address, and then do it in a loop so that every matrix multiplication happens, right? Basically, if you have a single matrix multiplication instruction, software is a lot easier to build, meaning the compiler, but hardware is a lot harder to build. And then there's also the issue of latency of simple versus complex instructions. A simple instruction like add or not can take very quick, but complex instructions like a matrix multiplication can take thousands of machine cycles, right? Or maybe millions of machine cycles, depending on the size of the matrix. So there's another trade-off over here. And this can be potentially optimized in hardware versus software. So who does the optimization becomes interesting at this point. So there are a lot of interesting trade-offs. We're not going to go into all of the possible trade-offs over here, but this opens a big can of worms, actually. I'm going to pictorially demonstrate it in a couple of slides when we talk about data types, because opcodes are also very tightly coupled with data types, as we will see. I'll discuss this in more detail when we talk about data types soon. So in LC3 and MIPS, there are three types of opcodes, and we don't have really fancy instructions like this. Basically, we have operate, data movement, and control, and we're going to look at them in this lecture, but no fancy instructions. Instructions are relatively simple. That's why these instruction set architectures are called simple instruction set architectures or reduced. I don't like the word reduced in general, but for historical reasons, people call it reduced instruction set architectures, simple instruction set architectures in general. So for example, let's take a look at opcodes in LC3. This is the opcode, right? This is all the 16 opcodes in LC3 from your book. And you can see that there's 16. One of them is reserved. And they're all very simple. You can look at every single instruction, and we're not going to study it, of course, in this course. You can study it if you look at your book. But those are the opcodes in LC3. In LC3B, this is the, let's say, evolution of LC3. It became byte addressable, and it's also added another opcode, XOR. As you can see, it removed the LDI instruction, which we're going to talk about, load indirect. Don't worry about that right now. But and then it created another unused opcode. So there are two things I want to mention in this slide. ISAs evolve, instruction set architectures over time evolve. It's not a static thing. Even though somebody defines this interface and people write programs on it, over time you can add instructions and you can change the ISA. Of course, you should be careful, right? If you, for example, do something such that it breaks the older programs, meaning older programs do not execute anymore in the newer machines that are built with the newer ISA, then you're basically breaking backward compatibility. And if you break backward compatibility, what happens is older software that assumed one ISA now don't necessarily work in the newer version of the ISA. And if you have a lot of software that is based on the older version of the ISA, and if you break backward compatibility with that software, then you may not be able to succeed in the future generations of your hardware, because your future generations of your hardware will not execute the older software. And people who designed the older software can say, forget it, I'm not going to buy the new hardware because I have to do all this work to actually compile into this new hardware that has a new interface. And as a result, you may actually find yourself not so effective or not so, let's say, profitable in your new hardware. So whenever you change the instruction set architecture, let me go back to the slide because the slide is very instructive, I think. Whenever you change the instruction set architecture, don't forget that there's software that was written assuming the old instruction set architecture. So you should be very, very careful. You should provide a path for that software to migrate to the new instruction set architecture. Or if you say, okay, forget about that software, then you basically run the risk of people not using your new instruction set architecture and new hardware. And there's some history over here. Intel, for example, in late 1990s, early 2000s, basically they said x86 architecture is a very complex architecture. We want to start from a clean slate, and we're a big company. So we're going to design our new architecture called IA64, Intel Architecture 64. So they redesigned the architecture completely, and the architecture was completely different from x86. And it was actually a very nice architecture. But unfortunately, a lot of people did not resist it, basically did not buy the new machines that are IA64. They were basically still buying machines that were x86 based, old x86 based, because they didn't want to recompile their software, rewrite their software, re-optimize their software to the new ISA. And it's very understandable because x86 has more than 40 years, at that time, more than 30 years of history. And people have designed a lot of software over the course of those 30 years. As a result, does it really make sense for people to actually change to a new ISA? And the answer is normally no, because it takes a lot of software effort to do that. So interestingly, AMD at that point in time came up with the AMD 64-bit extensions to x86. So they did not change the architecture completely like Intel did. So they just added to the architecture 64-bit extensions. And that was what became successful, basically. Everybody adopted AMD's x86 64 extensions. And Intel had to adopt AMD's x86 64 extensions so that they can continue to be competitive in the market. So that's the power of ISA, basically. That's the power of this interface. This interface may look like just an interface between hardware and software, but it really supports all of the software ecosystem that's on top of the interface. So if you change it, if you make a mistake by changing it too much, or by changing it in a backward incompatible manner, or by changing it in a manner that was backward incompatible, but old programs run very slowly, then you still have a problem, basically. Okay, that's why ISA design matters a lot, actually. So let's take a look at MIPS. I've given you LC3 instruction types. So, okay, these are opcodes in LC3, and we're going to look at more examples of this. MIPS instruction types consist of 3 types: R type, I type, and J type. Actually, we've seen all of them yesterday. We're going to see again them today. R type is basically register-to-register operations. I type is register plus immediate operations. And J type is basically just immediate. There's no register over here. And jump was one example. That's why it's called J type, right? Remember, jump was jumping to program counter concatenated with the 26-bit immediate sign extended and shifted left by 2, right? If you recall one of the last flights, that's the definition, semantic definition of the jump instruction. And these are the MIPS R-type instructions from your book. You can see that opcode is 0 in MIPS R-type instructions, but funct defines the operation. So let me go back to this here. Opcode is 0, but funct defines the operations. So this is actually a trick instruction set architecture designers play. You set an opcode to the value, and then you have another opcode field based on that value. If this opcode is 0, interpret these last 6 bits as opcode also. And that is basically the function that should be executed in the ALU in these register-to-register operations. And this is basically for all instructions that have opcode 0, this is what happens when funct has different values. Function has different values, as you can see. For example, shift left logical, jump and link register, break, system call, move to high. We're going to look at some of these. Divide unsigned, and you keep going. You can see subtract, add, XOR, NOR, set less than, etc. And you can see that not all 64 possibilities of function is exhausted. So there's room for adding more instructions into the ISA. Whenever you design an ISA, it's always good to have room for adding more instructions, potentially adding more data types, etc. Okay, you can find a more complete list of instructions in Harrison Appendix B. And certainly you can find the full list of MIPS instructions in online. And I think we have a MIPS cheat sheet linked from our course. Okay, so that brings me to data types. We talked about opcodes and instructions. Let's talk about data types. So data types are actually tightly coupled with instructions. Data types are types of data for which you have instructions in the ISA to operate on. This is one definition of data type. And ISA supports one or several data types. For example, LC3 only supports 2's complement integers. We did not cover 2's complement integers. This is actually in part of your readings, but I'll define it right away. This is actually one way of representing signed numbers such that addition becomes simple, if you will. So this is the representation, basically. You have a positive representation. Negative of a binary value x is the bitwise not of the x plus 1. That's basically how you negate a value, x, okay? And this works nicely for both negative integers as well as positive integers. That's why 2's complement integers actually are very good. There's also a value integer called 1's complement, which I'm not going to cover, where this doesn't hold. Basically, what you do for negative is different from what you do for positive, which is very unintuitive. That's why people develop these 2's complement integers. And now you can convince yourself that if this is the definition of a negative value, you can convince yourself that x plus negative x is equal to 0, actually. If you actually do the, binary addition of x plus negative x, assuming negative x is not x plus 1, then you get a 0 value. That's the beauty of 2's complement integers. And LC3 is an interesting, a very simple instruction set architecture that supports only 2's complement integers, basically. Okay. MIPS, on the other hand, supports 2's complement integers. 2's complement integers are supported by essentially all computing architectures today, if you will. But it also supports unsigned integers. It also supports floating point operations. Floating point operations, unsigned integers are basically integers that are not signed, basically. Everything is greater than or equal to 0. Floating point is basically fractional values. How do you represent 1.567, for example? Do you have some native support for that? And there is a format called floating point format. There are actually many versions of floating point formats that basically specify how you would represent these fractional values. So, for example, if you're doing scientific computation, if you're doing neural network training, for example, you need to use floating point values significantly so that you can converge to some result, or you can actually be precise enough, right? Because you need these floating point values. And the question is, does the hardware inherently support these floating point formats? And are there instructions in the ISA that operate on these floating point formats? And in case of MIPS, the answer is yes. Now, interestingly, historically, MIPS was a very reduced, small instruction set architecture. Initially, MIPS did not have floating point. Later, people said, oh, programmers need floating points. And if you want to be a successful instruction set architecture, we need to add floating points. And that's what they did. They added floating points. And that's another example of evolution of an ISA. An evolution of an ISA is almost always dictated by the needs by the software. Software needs some data types and operations, and the ISA adds them over time. Okay, so basically, again, there's a trade-off. There are trade-offs involved: hardware complexity versus software complexity. So if you have more data types and more complicated data types, hardware becomes again more complex, right? Because hardware needs to support these data types. For example, a matrix can be a data type. A multidimensional array can be a data type. A doubly linked list can be a data type. You can support all of them at the cost of hardware complexity. And if you support them, it's nice for the software because the software can directly map a doubly linked list, directly map a matrix into a data type called matrix in the hardware, right? So basically, there's a huge trade-off between hardware versus software complexity. And again, it's the same trade-off as we discussed in instruction, latency of operations supported on support versus unsupported data types. We will see that later on when we talk about some specific instructions. But for example, if you have an unsupported data type, for example, you don't support floating point, how does a programmer express fractional values using 2's complement integers? There's no fractional value. They need to basically jump through a lot of hoops to make sure that they can manipulate numbers that are fractional, because the hardware doesn't represent them natively. They have to do it in software and emulate them using unsigned integers or 2's complement integers. As a result, software blows up, meaning you need to have a lot of operations to represent the values and also operate on the values. But hardware becomes simple, of course, in that case, right? Hardware becomes more complex if you add floating points, which makes the life of the programmer easier, and also latency of those floating point operations lower because they're supported in hardware, because the hardware has specialized functional units that can do floating point operations. Similar with matrix multiplication operations, for example. So we will see more examples of this as we go along, but I'll give you even simpler examples from LC3 and MIPS toward the end of this particular lecture. So basically, why do we have different data types in ISA? Essentially, this is an example of the programmer microarchitect trade-off. And if you want to have more data types, the reason is to make programmers' life easier. The advantage of more data types is it enables better mapping of high-level programming constructs to hardware, essentially. Hardware can directly operate on data types present in programming languages. As a result, it can use only a small number of instructions, and the code size becomes smaller. And the instructions may be faster because they're natively supported by functional units in hardware. Some examples. Do you have matrix data type? Or do you use individual multiply, add, load, store instructions on unsigned integers or signed integers, for example? Do you have a graph data type that basically supports graph operations, graph analytics that is commonly used in software? Or do you operate on graphs using individual load, store, and add instructions that where the hardware doesn't have any understanding of graph, it just understands load, store, add, multiply, etc. Right? So that's the trade-off, basically. You can see that these operations on the left, matrix and graph operations, are complex. These are very simple. But if you want to actually manipulate a matrix, this is easier for the programmer, whereas this is much harder for the program. The disadvantage, of course, it's more work for the microarchitect. Now, microarchitect needs to implement the data types and the instructions that operate on the data types. Okay, now let's couple these things together, because data types and instruction complexity are actually very much coupled to each other. They're coupled tightly to the semantic level or complexity of instructions. And here I will introduce the concept of semantic gap. Semantic gap is basically how close instructions and data types are to high-level language. You have a high-level language, Python, C, Java, pick your favorite. How close are your instructions in the ISA, in the hardware-software interface, and the data types are to the constructs in the high-level language? I have a doubly linked list in Java, for example. Is there a doubly linked list in the ISA? That's the question, basically. Okay, so if you have complex instructions and data types, then you have a small semantic gap. Then the ISA is closer to high-level language. For example, the ISA has instructions that can insert it into a doubly linked list. It can multiply two matrices. For example, VAX ISA had this actually. VAX ISA had the doubly linked list instruction as well as a data type. There are different instructions: insert instruction, remove instruction, search instruction. And then it also had multidimensional arrays, basically. It could operate on multidimensional arrays. On the other hand, the exact opposite, you have simple instruction and data types. Now you have a large semantic gap compared to the high-level language. You support only primitive operations: load, store, multiply, add, NOR. Sometimes even multiply is frowned upon, let's say. It may not be primitive enough, right? Because multiply, you can always express it as shift and add, right? But of course, people figured out that multiply is so important that you cannot let the programmer express it as shift and add only. So early RISC machines, reduced instruction set architecture machines, had only integer data type and simple operations. And they quickly figured out that this was a bad mistake, because programmers need more than integers. They need floating point, they need multiplies. Initial RISC machines actually didn't have multiplies also. They didn't have byte adjustable operations. So over time, they kept adding and adding new data types and complex instructions. Let's take a look at the semantic gap pictorially a little bit. I like looking at this thing pictorially because I think it explains things better. Basically, we're talking about how close instructions and data types are to high-level language. So let's draw the line for high-level language over here. Pick your favorite language again, Python, if you will. And then we have hardware control signals. In the end, what a machine does is take the high-level language, what a system does is takes the high-level language and maps it to the hardware control signals and executes, ensures that hardware control signals do what the high-level language specifies things to do. But of course, we go through an ISA, as we discussed, right? Instruction set architecture. The question is, where is that ISA? Is it closer to the high-level language, or is it closer to the hardware control signals? So an ISA with complex instruction data types is closer to the high-level language, and we call that a small semantic gap. And complex x86s, for example, definitely small semantic gap. But VAX, some older ISAs actually have even smaller semantic gaps. Some machine learning accelerators today have even smaller semantic gaps so that they can map the machine learning constructs to the hardware accelerator. If you look at the simpler ISA, meaning ISA with simple instruction and data types, it's much closer to the hardware control signals and large semantic gaps. So this length of the semantic gap, if you will, tells you how much work is it for the compiler to compile from a hardware language, high-level language, to the NISA. Here, there's small work. Here, there's large work. Here, the hardware does the large work, as you can see, because it needs to execute this ISA with complex instruction data types and map it to the control signals. So this pictorial view was very nice because it tells you how much work the software, meaning the compiler or the programmer, needs to do versus the hardware needs to do. Here, hardware needs to do little, software needs to do a lot. So keep this in mind. We may revisit this in later lectures. And this is really the fundamental trade-off in when you're designing an ISA. This applies to addressing modes as well, actually. It applies to opcodes, it applies to data types, it applies to addressing modes. As you make them more complex, you reduce the semantic gap, you make life easier for the programmer, you make life harder for the hardware designer. As you make them more simple, you make life harder for the software programmer, meaning the compiler designer, or if you're an assembly programmer, for example, and you make life easier for the hardware designer. And this is a very fundamental trade-off in computer architecture, where how you change the trade-off between the programmer and the microarchitect. Okay, I'm spending a lot of time on this because this is really fundamental and important. This is the last slide where I will talk about essentially what happens with complex versus simple instructions plus data types. So if you have complex instruction, an instruction does a lot of work, many operations. If you have a simple instruction, instruction does little work. Basically, it's a primitive using which complex operations can be built. And you can see some complex instructions over here, and you can see some simple instructions over here. And again, multiply, You may be fuzzy on multiply. Is it really simple? Is it complex? But definitely compared to these, it's simple. So computing FFT, fast Fourier transform, could be an instruction. String copy could be an instruction. Video encoding, decoding could be an instruction, for example. So these things are high-level language constructs, as you can think. So the advantage of complex instruction data types is, aside from mapping it nicely to the software, you also have denser encoding. You have smaller code size, basically. You can encode one a matrix multiplication with a single instruction, right? You don't need to spend millions of instructions on it. Smaller code size, as a result, you have better memory utilization. You can save off-chip bandwidth, better cache hit rate. You will see all of these later on. Better packing of instructions. So this denser encoding is very important. You normally may get very high performance. But, and also you have a simpler compiler, because the compiler doesn't need to optimize small instructions as much, right? As we discussed earlier. But the disadvantage of complex instruction is you have larger chunks of work. As a result, compiler has less opportunity to optimize. You can think of it that way as well. So a compiler says, basically, okay, this is your instruction, hardware, do whatever you need to do with this instruction. I cannot optimize it because you provide me one instruction that says matrix multiply. Now I cannot reorder the operations internally. Okay, so that's the downside of larger chunks of work. But there's another downside, which is more complex hardware, right? Translation from a high-level ISA to control signals, and optimization needs to be done by hardware. Okay, so we may get back to this. If you didn't understand this fully, that's okay, because this slide is a little bit more advanced than the prior slides. I hope you understand the concept of the semantic gap and its implications on the programmer and the hardware designer. Now, let me give you a fun example. This is an example of a binary coded decimal. Has anyone heard of binary coded decimals? I don't know. I don't see any hands raised. Okay, maybe there's a hand raised. Okay, that's good if you've heard of it. x86 ISA actually has this data type, which is not used much today. But basically, you encode a decimal digit with a fixed number of bits. And the best way of looking at it, or one way of looking at it, is by encoding this clock. So this is time. It's 37 past 10, and we're 49 seconds into the 37th minute. And basically, for each decimal digit, we have a binary representation. And you can see the binary bits over here, 1, 2, 4, 8. You can see that we need 2 bits to represent 1 to 2 over here, right? Or 0, 1, 2, if you will. We need 4 bits to represent 0 to 10 over here. We need 3 bits to represent whatever needs to come over here. We need 4 bits to represent over here. Sorry about that. And you can see that the dark shaded ones are actually what's encoded. So to encode a 1, you need to dark shade this one. This is 0, so none of them are set. This is 3, so 2 of these are set. 2 plus 1 is set, as you can see. This is 7, so these are set. This is 4, so only 4 is set. And this is 9, so 8 plus 1 is set, as you can see. So this is basically the binary coded decimal encoding. And this is an encoding that makes life perhaps a little bit for the machines to interpret decimal code. And people use this encoding in the past. They're not using it as much. But this is an example of a data type. And you can actually expose this data type in clocks. You can buy these clocks that encode things this way. So this is time, 12, 15, 45. And this is the same time encoding binary coded decimal. You can actually do this, 12, 15, and 45, as you can see. So it's very hard, of course, for a human to decode this unless you get used to it. But it's very easy for a machine to actually directly translate this to binary coded decimal to a decimal value. But this is an example of a data type. And I would say that the data type of this clock on the right is binary coded decimal, essentially. Okay, so this is fun. Keep that in mind. Let me talk about addressing modes, and then we'll take a break. We started a bit late, so sorry about that. So addressing mode, as we discussed earlier, is a mechanism for specifying where an operand is located. Basically, how do you calculate the address to get to the operand? And in LC3, there are 5 addressing modes. Immediate or literal, the operand is in some bits of the instruction. We've seen this constant, and we're going to see this again. So I'm going to go through this quickly. Register means that the operand is in one of the general purpose registers. And there are 3 memory addressing modes: PC relative, indirect, base plus offset. Base plus offset we have seen actually yesterday. PC relative and indirect we're going to see today. MIPS has pseudo direct addressing for jump and JAL instructions, which we have actually seen in the last minutes of yesterday's lecture, but it does not have indirect addressing. So MIPS especially works on base plus offset addressing, as we will see. Okay, so basically we have similar trade-off over here. Why do we have different addressing modes? To make programmers' life easier. But this makes microarchitects' life harder. So the advantage, again, it enables better mapping of high-level programming constructs to hardware. Some memory accesses are better expressed with a different mode. You use reduced number of instructions and code size to express these addresses. For example, array indexing. Base plus offset is very good for array indexing. If you don't have base plus offset addressing mode, you'll have difficulty. Well, not difficulty, but you need to use more instructions to calculate the address. Pointer-based addresses, injection actually enables that because when you do pointer-based accesses, you go to a memory location and you take that memory location and you use that as an address of another memory location, right? Now you have indirection, right? And if your hardware supports this indirection, supports these pointer-based addresses, accesses, then you can actually map the software more easily to the hardware. You can use fewer instructions and smaller code size. Sparse matrix accesses, we discussed this actually in Sean Lee's lecture, right? A lot of neural networks are operate on sparse matrices today. Do you support sparse matrix accesses in hardware? Basically, how would you support that? You would quickly be able to find a non-zero element in a sparse matrix. Of course, you can make your sparse matrix a data type also in your system, right? Addressing mode is basically how do you address that data type? Okay, of course, the disadvantage again, more work for the microarchitect and more options for the compiler to decide what to use in this particular case. Which addressing mode do you use so that you get the best performance, for example? Okay, so semantic gap applies to addressing modes as well. Now, how close are your instructions, data types, and addressing modes are to high-level language? So semantic gap, again, is not just instructions, it's not just data types, it's also addressing modes. So keep that in mind. More complex ISAs have smaller semantic gap, meaning complex instructions, complex data types, and complex addressing modes, and many of them. Okay, so there are many trade-offs in ISA design. We're not going to cover all of them. Actually, I will point you to some lectures. We're going to talk about execution model in a couple of lectures, actually. We assumed von Neumann, for example. Von Neumann is a trade-off in ISA design also. What's your sequencing model? What's your processing style? Do you have sequential processing or do you not have sequential processing? So we're going to question this later on. We talked about instruction length, format, types. Well, we didn't talk about instruction length a lot, actually, but you can have variable length instructions versus fixed length instructions. This basically changes your decoder complexity, etc. We talked about instruction complexity versus simplicity, data types. We did not talk about number of registers as much. We talked about addressing mode types, but you can see there are many, many, many other things over here. Even today, voltage and frequency scaling actually is part of potentially the ISA today. So there are many system level issues also. So after we take a break, I'm going to talk more about instruction types and addressing mode types. And we're going to go more into examples of these different types of instructions, operate, data moment, and control flow. And we're going to see some example trade-offs in a limited manner so that we can understand these trade-offs, at least within the scope of the ISAs we're examining in a better way. Okay, so but now let's take a break. Actually, let's take a 10-minute break again. So let's be back a little bit after the bell rings around, I think 15:21, let's say. Oh no, not 21, sorry. 15, I cannot calculate, 15:17. Okay, and I'll see you in 10 minutes.
Also Input muss halt eine Ordnungsfrage haben. Und dann wird der Klick auf das A. Aber macht es einfach durch A, weil das ist einfach das Virtual Logic. Und der Logic. Komischerweise das Handy zuletzt nicht verfallen. Wieso? Bitte? Ganz anders als Backup wieder. Da kann ich auch nicht einfach versuchen herauszufinden, was für eine Seite ist. Wie viel Seite ist.
Okay, I think it's time to get back. So let's continue on. Sorry, I need to put on mic. Okay, so we're going to continue with operate instructions. As I said, ISA design is fascinating and there are a lot of trade-offs and there's a lot of history behind it. I gave you some example history where even an extremely strong company like Intel was not able to change the ISA and they had to resort to an incremental improvement over x86, right? That's why ISA is so strong, because there's a lot of software built on top of this interface. Now let's take a look at these instructions and then how they operate. Now we're going to be, let's say, less theoretical. The first part of this lecture was kind of theoretical. It talked about trade-offs and the semantic gap, high-level language, etc. But now we're going to look at real instructions in LC3 as well as MIPS and how they get executed. You've seen some of that, but we're going to see more of that today. We're going to start with operate instructions. Operate instructions are essentially instructions that execute in the arithmetic logic unit, right? In LC3, there are 3 operate instructions. It's very small, basically. It's such a small instruction set. Not is a unary operation. It has 1 source operand. And, okay, my slides. Okay. Basically, it's bitwise not, as we discussed. Add and AND are binary operations. They have 2 source operands each. And add is 2's complement addition. AND is bitwise AND of 2 registers, or 2 registers, or 1 register and 1 immediate value, as we will see. In MIPS, there are many more, of course. MIPS is a real ISA. As a result, they have to cater to the needs of the higher level languages more. And most of our type instructions are binary operations. They're operate instructions. And okay, somehow my computer is freezing more than it needs to. Okay, for example, add, AND, NOR, XOR. There are I-type versions also with 1 immediate operand of the R-type operate instructions, as we will see. That's true for LC3 also, actually, but LC3 doesn't have a separate encoding for these. LC3 actually plays a nice trick, as we will see, where 1 operand can be register or immediate. I actually mentioned that yesterday, but we're going to go into a little bit more detail. There's also F-type operations, which are floating point operations, which we're definitely not going to go into, but they're also extremely important, as we discussed, right? Now let's take a look at NOT in LC3. So this is NOT. This is the assembly code, as we have seen yesterday, for many instructions. This is the field values of a 16-bit instruction. And this is the machine code, as you can see, the 15-bit encoding of this particular instruction. So there's nothing magic about it. You have a destination register and a source register, and then an opcode. And the remaining bits are specified by the ISA to be all 1s. And this is how it operates, basically. Basically, I'm just showing you the operation of the operation portion of it in the ALU. You basically read the source register into the A port of the ALU. And then this doesn't matter what you read over here, because you set the function of the ALU from the finite state machine that determines the logic, that determines the control logic signals as not. And once the control signal is not to the ALU, it doesn't matter what the B input is. It basically takes the complement, bitwise complement of the A input and generates the result. And the result gets connected through the bus, if you remember the processor bus. And then we write it back to the register file into the destination register. For that, we need to enable the load destination register. And the destination register's address is determined by the DR bits over here. And clearly, the source register's address is determined by the IDSR bits. So we know exactly how this not executes. It's actually simpler than what some other instructions that we've executed yesterday. I'm not showing you the complete machine over here, but just the part that requires us to carry the operation itself. Okay, so this is funny and interesting, but there's no not in MIPS. If I ask you the question, how is it implemented? Any takers? If you don't have a not operation, how would you implement not? Maybe someone in the, okay, I see a hand raised over there with someone in an orange cap. Okay, let's see if we can deal with this hybrid mode. Let's see if I can hear you first, I guess.
Hello?
Hello, yes, I can hear you.
Okay, you could multiply, or you could interpret the 32 bits as a 2's complement integer, signed, multiply by -1 and subtract 1.
I see. Okay. Yeah, maybe you're thinking more. Yes, certainly. I think you can potentially do that. It's certainly possible to do that. And by doing more operations, you can get to a not. And I believe that actually. But there's a simpler way actually. And someone on Zoom proposed it. And it's basically doing NOR. And the idea is you don't have not, but you can still do a single instruction. And the instruction is NOR. If you do NOR of, for example, if you want to take the not of R5, you do NOR of R5 and R5. And if you do NOR of R5 and R5, essentially what you get is a not. And MIPS has NOR. And that's the reason why they don't have MIPS. But there are multiple ways of doing it, as you said. There could be more longer ways of doing it also. But this is fun, basically. You don't have to have every single operation. You just need to figure out how to enable the operation using other operations that are provided by the ISA. And we will see that again. So we're already familiar with LC3's add and end with register mode. And we're also familiar with R-type in MIPS. Now let us see versions with one literal, meaning one immediate operand. We want to add a register to an immediate value and then store the result in a register. And we will use subtraction as an example. The question is, how is it implemented in LC3 and MIPS? I'm going to give you some examples. But recall before we move on, this is the register to register operate instruction format in LC3. Basically, what this does is SR1 plus SR2 gets the SR1 op SR2. It could be plus, it could be and, depending on the op field over here. Gets the you do that operation and then you write the result in the destination register. And we will see the difference between this and when the second operand is an immediate, which is this basically. So let's take a look at add and end. It looks very similar actually to prior encoding. We have destination register here in the same place, source register 1 here in the same place, but instead of source register 2 and some 0 bits over here, we have immediate 5. And this bit became 1. So basically, and we use the same opcode basically. Opcode is the same op as register mode at, and opcode is the same opcode as the register mode and. Basically, the way this instruction operates is SR1 op sign extended immediate 5. So immediate 5 is 5 bits, right? It's a signed value. You extend it to 16 bits because you're going to add it to a 16-bit register in this particular case. Basically, that's what sign extension means. You take the top bit and you replicate it such that all 16 bits are filled. Makes sense, hopefully. That's the idea over here. So basically, that's the operation. Destination register gets the value in SR1 plus sign extended immediate 5 bits coming from the instruction. If you want to do an AND, it's the same thing basically. The destination register gets the value in SR1, bitwise ANDed with sign extended immediate 5 over here. Okay, hopefully that makes sense. And we've already discussed source register, destination register, and immediate 5 is literal or immediate, and we sign extended to 16 bits. So hopefully you understand the notion of sign extension. There's also the notion of 0 extension. Basically, you have only 5 bits encoded in the immediate 5 over here because your instruction cannot encode 16 more bits over here. And we want to extend it to 16 bits. What do? We sign extend it because this is a signed value. We interpret it as a signed value. That's what the ISA tells us to do, meaning that we replicate the sign bit at the most significant bit through bits, I guess, 16 through 6 in this particular case. If you wanted to 0 extend it, we would just fill those bits with zeros. But in this case, the ISA tells us to sign extend. This is the ISA definition of the semantic operation of add and AND. So now we have operate instruction operating using one register and an immediate. And let's go back to the encoding previously. So this was the encoding of the operate format when we had 2 registers. And the main difference is over here, right? Bit 5 is 0 over here, indicating that the remaining bits specify a source register 2 in the bits 2 through 0. If bit 5 were 1, then the remaining bits basically specify a 5-bit immediate value. So the ISA designer played a nice trick over here. If the op was add, if the op is add or AND, you look at bit 5. If the bit 5 is 0, then the second source register, second operand is a source register specified by bits 0 through 2. If the bit 5 is 1, as you can see over here, then the second operand is a sign extended immediate 5-bit value specified by these 5 bits. So this is how you can play tricks in encoding instructions so that you can actually encode more powerful instructions. x86 actually plays a lot of these tricks. You actually have many different ways of encoding different things in x86. And based on the opcode, you look at a different field, and based on the value of another field, you look at a different field, and based on the value of that field, you look at a different field, so that you could decode the instruction completely. And of course, this makes decoding more complex. So as you keep adding more bits to interpret other bits, then the decoding of an instruction becomes more sophisticated and more complicated. Okay, so this is the assembly and machine code of add with one literal, basically. This is an example. Add into R1, R4, plus -2. -2 is the immediate that's encoded. And this is how, the encoding of the instruction, as you can see. And this is the machine code. You can convince yourself that this is correct. And this is very easy to verify. It's correct, actually. And this is how it gets executed. So let's take a look at the execution of this now. Remember, for add, we needed to go through the ALU. So we had source register 1 and source register 2 coming from here. And then we added them and we put the results into the destination register. Here, we're going to take source register 1 as the input, A input of the ALU. But as a second input, we're going to pick bits in the instruction register, bottom 5 bits. We're going to sign extend them to 16 bits, as you can see. If the bottom 5 bits are 1, 1, 1, 1, 0, which is -2 actually. And if you sign extend them, you will get this. And then you're going to go through this mux. And this multiplexer will be controlled by bit 5 of the instruction register, which is the magic bit 5 we discussed, right? If bit 5 is 1, you select the sign extend immediate as a second input to the addition. Otherwise, if bit 5 is 0, you select the source register 2 as a second input to the addition. That's why we have this mux in the data path. So it's beautiful, basically. We're building these logic structures that obey our instruction format, as well as the specification of the instruction. And the finite state machine in the control logic needs to generate an add signal to the ALU, basically the particular encoding of the add, such that the ALU does add on A and B, essentially. And the result needs to get stored into the destination register. So that's how this beautiful instruction gets executed. And also, you now see how an operate version, a register version of this instruction gets executed, purely register version, register plus register version. Okay, so hopefully that's clear. And we were looking at this part of the system when I showed you this slide, actually. So let's take a look at this. So this is where sign extension happens. As you can see, you take the bottom 5 bits of the instruction register, sign extended, feed into the source register 2 mux over here, and that's controlled by bit 5 over here. And based on the value of bit 5, you select either the sign extended immediate or source register 2, and then do the addition. That's the same. That's true for AND also, actually, except AND specifies this ALU control signals and not add. Okay, and I've already said this. Basically, you select either immediate or register as a second input to instruction, and you know what that control signal is exactly. It's directly coming from instruction register bit 5. Okay, you actually have very similar instructions in MIPS as well. You have instructions with one literal in MIPS as well. These are called I-type MIPS instructions. MIPS doesn't play the trick that I showed you. It basically has a completely different instruction encoding that's separate from R-type. And again, this is the choice of the instruction set designer. Basically, you have 2 register operands and an immediate. And the reason they chose this actually so that they could make the immediate larger, as we will see. So some operate and data movement instructions are also using this sort of format. Okay, so this is the opcode basically. Sorry, this is the encoding. You have the opcode, you have RS, RT, and you have the immediate. And you can see that the immediate is 16 bits. Basically, you can specify a much larger value within that field right now. It's on the order of 2 to the 16, right? As opposed to what we saw 2 to the 5 in LC3. So you can add much larger immediates right now. So opcode is the operation, RS is the source register, RT is, depending on the instruction, it's destination register. For example, in add I and load word, it's destination register, and it's source register in others. So these are idiosyncrasies of the ISA, as you can see. You need to know this so that you can write you can create a machine for the ISA, or you can write programs for it. But that's how it goes, basically. And immediate is a literal or immediate value that you're going to add or operate on, if you will. Let's take a look at add immediate. This is the MIPS assembly of the add immediate, very similar to the LC3 assembly, except encoding will be very different, as you can see. The encoding, it looks like this, opcode, and then RS, RT, and the immediate over here. And you can see that this is the RT gets RS plus sign extend immediate. And this is the machine code. By the way, I think this opcode is wrong over here. I was going to say that, and this thing corrected me over here. This must be the correct one, because opcode cannot be 0, right? The 0 opcode is actually requires this last part to be funced. So this is an I-type instruction. 0 opcode happens only in the R-type instructions. So we need to fix this. This should be 1, 2, 4, 8, and hopefully one of the TAs will verify. I'm going to speculate to fix this opcode to be 8, but I believe it certainly cannot be 0 based on everything we discussed, right? Because 0 says that it should be an R-type instruction, as we discussed before. And then you have to think about the bottom 6 bits over here as function, right? Not the immediate. But opcode here is add immediate in this particular case, and immediate is specified by the bottom 16 bits over here. And in this case, it's 5. And this is a semantic operation, basically. RS plus sign extend immediate gets written to the value of RT. Okay, hopefully this is simple. And this is the machine code in hexadecimal if you're interested. Now let's take a look at how we can do subtract, something more interesting, basically. Now we know how to do add. How do we subtract in MIPS versus LC3? So MIPS assembly, let's say this is your high-level code, 1 addition, 1 subtraction. Basically, you use 1 addition, 1 subtraction, basically, assuming your variables are allocated to these registers. B and C are in S0 and S1, and D is in S2. This is what will happen, and the result goes into S3, which is an A. And there are some temporary registers that you can see you use. So MIPS is nice because it provides a subtract opcode for you. LC3 is not that nice. It doesn't provide you a subtract opcode, so you need to do the negation yourself. So basically, B and C are in R0 and R1. D is, assume that D is in R3. Basically, if you first need to negate D, that's the 2's complement of R3, basically negation of D. Remember, negation of D in 2's negation of a value in 2's complement is bitwise not, and then you add 1 to it. This is how we get minus D over here, because we don't have a subtract operation. So we basically add B plus C over here, and then add minus D to it over here with this add. So you can see that we wasted 4 instructions here. We spent 4 instructions to do the same addition, as opposed to 2 instructions to do the same addition. So LC3 was more costly because it did not provide a subtract instruction, meaning it did not map as nicely to the higher level language over here. So this is a very nice example, very simple, but very nice example of how an ISA semantic gap is farther away from the higher level language. It doesn't have subtract. It's a bit far away from the higher level language. So you need more work in your program, but the hardware designer's life is easier. They don't need to implement a subtract instruction. Okay, so this is basically our theory that we discussed earlier put into practice. Hopefully that's clear. So the trade-off is more instructions in LC3, but simpler control logic, simpler hardware. Okay, let's take a look at subtract immediate. MIPS assembly actually provides you with subtract immediate also. Basically, you can express this with a single instruction, sub I, in MIPS. That looks nice, right? In this particular case, sub I is actually not necessary in MIPS. You could have actually done it with add I with a negative immediate, right? Subtracting 3 means that adding minus 3, basically. And if you can encode the minus 3 with a negative immediate literal value in the instruction, you can do this. Clearly, we can do that because we have 16 bits to encode a value in MIPS, if you remember the several slides ago. LC3 actually is nice in this case because you can do the same thing in LC3. You don't need a subtract instruction for this particular case if your operand is minus 3, of course. If your operand was minus 256, you couldn't do this in LC3 because minus 256 doesn't fit in 5 bits. Because remember, the immediate is the last 5 bits at the bottom. But because -3 is nice, it fits into 5 bits. As a result, you can encode this nicely without wasting any instruction compared to MIPS. Okay, so now, of course, you may ask the question, what if it doesn't fit into 15, let's say the last 5 bits? Then you need to construct the value somehow, right? And we will see how to construct values using instructions soon in both LC3 and MIPS. Okay, so that finishes the operate instructions. There are clearly many more operate instructions that we discussed, but they're essentially the same. It's all encoding, semantics, how they operate, and different trade-offs. Let's now move into data movement instruction and addressing modes, because this is going to be something new that we didn't discuss a whole lot. Well, we discussed some of addressing modes, but we're going to go into a little bit more depth. So in LC3, there are actually 7 data movement instructions. You can see LD, LDR, LDI, LEA, ST, STR, STI. So there are load and store versions, and then there's special LEA, load effective address, which is actually a data value construction instruction, as we will see. I don't like the name of load effective address. There's a specific purpose in mind when the ISA designer designed it. It's really you're constructing a value in a register, as we will see. Okay, the format is all the same basically for load and store instructions. You have an opcode, you have destination register or source register in bits 11 through 9, and then some address generation bits. And then the question is, how do you generate the address? Address generation bits tell you, opcode plus address generation bits tell you how you generate the address. And there are 4 ways to interpret the bits called addressing modes. Essentially, there are 4 ways of generating the address for load and stored instructions. There's PC relative, indirect, base plus offset, which we have seen, and immediate mode. So we will see all of them. In MIPS, there are only base plus offset and immediate modes for load and store instructions. So this is interesting. Even though MIPS is a more real and complex ISA, they made the choice to be more simpler than LC3. So not in all cases, an ISA is more complex than another ISA, basically. This is proof of that, if you will. So all ISAs are idiosyncratic in this sense because they're designed by humans. Okay, let's take a look at the PC relative addressing mode. We've actually seen an example of this before. So this is our load and store. These are the instructions that have PC relative. And this is the opcode as usual. This is the destination register or source register, depending on load or store, clearly. Load has a destination register, store has a source register. And this is the 9-bit offset that is used as a PC relative offset, as we will see, to calculate the address that we're going to load from or store into. So op is opcode, as we discussed. For load, it's 0010. For store, it's something else. DR is destination register and LD, and SR, these values, these bits specify the source register and ST. And this is the semantics of the load instruction. Basically, destination register gets the value of memory location at this address. Let's take a look at how that address is computed. You get the incremented PC, which is the address of not this instruction, but the next instruction. That's why we increment the PC early on in the fetch cycle. And then we add to it plus sign extended 9-bit offset over here. So that's basically based on the address of the instruction, you calculate an address. So the value is located from an offset from this particular instruction in memory. That's the idea, basically. So this is called PC relative addressing mode. It's used in many ISAs, and this is how it's used in LC3, as you can see. The same is true for store, basically. Store calculates the address exactly the same way. It goes to the memory location, and basically writes the value of the source register to that memory location, as opposed to loading the value from the memory location to a destination register. So now you have one addressing mode. And let's take a look at how this is executed. So this is our LD. This is our assembly. You can see that there's a 9-bit offset over here. And this is our field values. This is the machine code, as you can see. And this is how it gets executed, basically. So let's go through the step by step. You need to evaluate the address at some point, right? Evaluation of the address is done by taking the incremented PC, this is PC plus 1, adding to it a sign extended 9-bit offset coming from the instruction register, as you can see. And then after doing the addition, supplying the result of the addition to the memory address register. Now, memory address register has the address that's computed this way in the data path in LC3. And again, we know exactly how to do this, right? I've actually shown you examples. We're going to look at the full data path in a little bit as well. Okay, sorry about that. Now, memory address register has the address. We evaluated the address, calculate the address. We wait for memory. We set the memory to read mode. Memory at some point returns the value into MDR, memory data register, and we take that value and place it into the destination register by setting the load destination register signal. And the destination register is encoded, its address is encoded by these bits, as you can see over here. So again, nothing is magic. We need to have data path components that calculate the address. We need to have data path components that enable us to read memory. We need to have data path components that enable us to get the data from the memory into the register file. And we have seen this LC3 data path. I'm just showing you parts of the LC3 data path over here. And again, as with all offsets, like the immediate, as we discussed, the memory address can be only 256 far away, 256 addresses larger, or 255 addresses larger, or 256 addresses smaller than the location of the load or store instruction, because this is PC relative. Remember, program counter is the address of the instruction. It can only be as far as PC plus 255 and PC minus 256, meaning that you cannot address the entire memory this way. Your data needs to be very close to where the instruction is. So this has limited capability, basically. The PC relative addressing mode cannot address far away from the instruction as a result. So we develop other addressing modes, as we will see. Okay. So that's one of the reasons for the indirect addressing mode. Let's take a look at indirect addressing mode. Indirect addressing mode is actually very nice for pointer chasing, meaning if you have linked data structures and you're going through a linked data structure, indirect addressing mode enables you to do indirection nicely. And it's natively supported by LC3. If you go back to where this could be useful in cases where your program and data are co-located together, and your program is here and data is close to it, and you can address your data directly from your, very close to your program, essentially. So clearly, indirect addressing mode may be more powerful from a high-level language perspective. And this is the indirect addressing mode, essentially. It looks very similar, right? You again have PC plus offset, a PC offset over here. You have an opcode and destination register, source register, depending on the load and store. So what's different? Let's take a look. The difference is address calculation and opcode. So opcode is different. LDI, LD indirect, STI, ST indirect. DR is destination register, and SR is source register in respectively LDI and STI. This is what's different, basically. How the address is calculated and how the memory is accessed. So destination register gets the value by accessing memory twice. What do? First, we have the PC relative addressing, PC plus offset, sign extend offset, just like we did earlier. We calculate that address. We go to that memory location. We take the value in the memory location, interpret it as an address, and go to the memory location with that address again, and then get the value in that memory location. So this is indirection, basically. We calculate a PC relative address, go to memory, treat the value in that memory location as an address, and go to memory again, and then get the data value. So there's a level of indirection involved over here, which is helpful for pointer chasing, as we discussed. And store is essentially the same, except it stores the value to that location. Okay, so this hopefully is interesting. And you can see this is the encoding, machine code. Let's take a look at how it gets executed. It's very similar to what we have seen before, except it has more steps. Basically, we have incremented PC. We have sign extended 9-bit offset in the instruction register. We add them, calculate the address. This is our first address. And then we put it into the MAR, memory address register. We read the memory. The data gets loaded into MDR. And then MDR, you take the value in the MDR and put it back into MAR so that you can read the memory again. We read the memory again, and then you get the value in MDR and put it into the destination register. Basically, the difference is another level of indirection so that we can treat the memory location that we access first as an address so that we can access memory with it again. So think about pointer chasing when you calculate a pointer, when you access a data structure, and the data structure is a pointer, and you want to dereference that pointer and get the value in that pointer. This is what this is useful for. But now there's also another powerful thing. Now the address of the operand can be anywhere in the memory. You're not limited to a particular offset that's specified by the instruction. It could be anywhere. By placing the pointers in the right place, you can access all of memory. So that sounds beautiful. So base plus offset addressing mode is the addressing mode that we have seen in LDR and STR. So I'm going to go through this relatively quickly. Basically, we've already seen this before: LDR and STR, load register, store register. And addressing mode is base register plus sign extended offset 6. And we have already seen it. And this is how it's executed. Basically, you take a base register, add to it a sign extended 16, sign extended, this is, I think, a 6-bit offset. And you load you put the value into the MAR, and then you do the memory read, and then the data is available in the MDR, and take the value in the MDR and put it in destination register. So this is very similar to what we have seen yesterday. So that's why I'm going through this quickly. But with LDR, again, the address of the operand can be anywhere in the memory because the base register can have any value, any pointer, basically. And as we discussed yesterday, this is very good for array indexing, right? Now let's take a look at address calculation a little bit more closely in the LC3 data path. So we have the global bus, we have the memory address register multiplexer, as you can see. So here's how we can calculate the address. This is the address computation adder, if you will. And you can see that there are different ways of calculating the address. So this sign extended 6-bit value gets added to SR1, and that's our base plus offset. This sign extended 9-bit value gets added to our base register, and that is useful for our LDI instruction as well as our LD instruction, right? So it's very basically all of these data path elements need to be supported in your data path, and your muxes become larger because now you need to support many different ways of calculating address. So that's one of the downsides of having many addressing modes. Your hardware becomes larger, and this is again a direct example of semantic gap. If your semantic gap is smaller, your hardware becomes much larger because you need to support many addressing modes that are supported by the high-level language, or that can support the high-level language. Okay, base plus offset addressing mode in MIPS. We've also seen this. In MIPS, LW and SW use the base plus offset mode. In MIPS, this is also called base addressing mode. I like base plus offset better, but MIPS calls it base addressing mode. And we've seen this high-level code in the past. Actually, we've seen the load version. This is the store version of it. Basically, it's a store word. And remember that we're indexing into an array and setting the second word to the value of this A variable. And basically, that's what we do. This is the address of the second word, because MIPS is byte addressable. Second word appears at address at an offset 8. And this is how we basically do it. This is the base plus 8 is the address. Base is stored in S0. And we write the value of register S3 into that memory location. And this is how it's encoded. Immediate is really the 16-bit offset. So this is a 16-bit offset in MIPS, which is sign extended to 32 bits. So it's very similar to LC3 again, except the offsets are larger. So you can specify even larger offsets in this particular case. So let's take a look at an example program in MIPS and LC3 and how it gets executed. So I'll go through this relatively quickly. You can study this on your own, but this is the high-level code. And this is the MIPS registers allocated to the different variables that you see in this code. And this is the MIPS assembly. So you have load word, add I, and store word. And LC3 is very similar. Again, you can see that there are corresponding instructions in LC3, load register, add. Even though it doesn't have add I in LC3, add still specifies an immediate value. Remember, LC3 played the trick of bit 5 specifying 0 or 1. Okay, is there a question? Okay, I don't hear anything, so I'll continue. Okay, so we've seen these addressing modes. That's why I'm going through this quickly. Let's take a look at immediate addressing mode in LC3. So this is the load effective address instruction. I call this data value construction instruction also, if you will. You will see what I mean. But basically, the encoding looks like this, and the opcode is like this. You have a destination register, and the destination register gets the value of PC, incremented PC, plus sign extended offset, 9-bit offset. Basically, you construct a value in the destination register that is specified by this calculation, program counter plus sign extended 9-bit offset. And that's the idea. So in this case, we don't go into memory. That's the difference from PC relative addressing mode. We don't go into memory. We just construct an address in the destination register. Essentially, LEA does an addition and writes the result into the destination register without going into memory. That's why it's called load effective address. So why is this useful? This is useful for constructing an address that could be useful for future address computations. I like the MIPS version of it, as you will see in a little bit. MIPS actually has a similar way, similar instruction, but it's much more powerful. You don't need to deal with the PC in that particular case. Okay, so let's look at LEA in assembly and machine code. Basically, it looks like this. Again, this is all specification from the instruction set architecture manual. And this is the execution. You have an incremented program counter, and you sign extend the bottom 9 bits of the instruction register and add to the program counter and place the result into the register file. Sounds good, right? You could potentially do this in ALU, except it's not done in ALU over here. It's done over here. Basically, sign extended 9 bits come from here. PC, incremented PC is here. You select the appropriate mux signal so that you select sign extended 9 bits and the program counter over here. You do the addition, and then you go through the MAR mux and then write the result into the destination register. So you can see the data path components involved in this, the sign extended part, this, and you need to ensure that this input is selected when you're executing LEA. You need to ensure this address 1 mux selects the PC input when you're executing LEA. And then there's an addition. And then you take this path, MAR mux, you select this input, you make sure, and then gate MAR mux into the result of the MAR mux onto the bus. And then the register file gets written with destination register and load reg signal. So that's how you execute LDA. Again, there's no magic. It gets executed with the data path components that we studied yesterday. Let's take a look at how similar thing can be done in MIPS using immediate addressing mode. MIPS is actually a more powerful instruction. Load upper immediate, loads a 16-bit immediate into the upper half of a register and sets the lower half to 0. This is how you can construct a value in a register, basically. It's used to assign 32 bits constant to a register, basically. This is a high-level code. Let's say this is your high-level code in your program. You assign a variable, assign this constant to this variable, and this is the MIPS assembly. You load upper immediate with this 16-bit value, and then OR the bottom 16 bits with this value. That's the idea, basically. So hopefully this sounds easy and nice. Here you load the upper 16 bits, or enables you to OR the bottom 16 bits that were set to 0 due to LUI specification. So with 2 instructions, you can do this 32-bit initialization that you can see over here. Okay, so this is something I would like to study, on your own. This is nice reverse engineering. Actually, a lot of people do in reverse engineering. If you're doing security, for example, you do a lot of reverse engineering of code. Basically, if you're thrown this code over here, even without the right side over here, by just looking at the instruction set manual, you can figure out what this code is supposed to do. What is the final value of R3, basically? I'm not going to say this, of course, to you, but basically what you need to do is you need to go through and figure out what these operations are, what the immediates are, what the encodings are, and basically do what the machine does, execute the instructions yourself. So basically, by knowing the ISA, by knowing the encoding, by knowing the instruction formats, you can figure out what any machine code and any string of 1s and 0s does. And in the end, the final value of R3 happens to be 5, and you can verify it on your own. Now, in the remaining time, let's talk about control flow instructions, which are actually important because without control flow, we cannot actually change the flow of control in execution, right? And we've already discussed some of them. We're going to discuss more sophisticated conditional branching right now. Basically, control flow instructions, what are those? They allow a program to execute out of sequence. Conditional branches and unconditional jumps are examples. Conditional branches are used to make decisions, for example, if and else statements. In LC3, there are 3 condition codes that are used, and we're going to talk about them. Jumps or unconditional branches are used to implement loops and function calls. So we've already discussed jump in LC3 and J, which is also jump in MIPS. We've already seen these. There are also variants of these, which I'm not going to cover in this lecture. Otherwise, we will talk about ISAs forever. But let's take a look at conditional control flow, because conditional control flow is very important, and how to handle this is very important. And there are 2 different styles of handling in LC3 and MIPS. Let's talk about them quickly. So LC3 contains what is called condition codes. This is very similar to x86, actually. You have these condition codes that are set by instructions, operate instructions. Each time, or in LC3, actually, it's more general. Each time an instruction writes to a general purpose register, there are 3 single-bit registers are updated, depending on the value that's written to the general purpose register. Oops, sorry. Basically, each of these condition codes are either set to 1 or cleared, meaning set to 0. So what are those? If the value that's written to the general purpose register is negative, N condition code is set, Z and P are cleared, indicating that the last value that was written to a general purpose register is negative. If the written value is 0, then Z is set and N and P are cleared, indicating that the value that was written was 0. If the written value is positive, P condition code is set and N and Z are cleared, indicating that the value that's written is positive. So hopefully this is very simple. You have 3 condition codes, 1 bit each, NZP. They're set every time you write to a register, and they're set based on the value that you write to a register, whether it's negative, positive, or 0. Okay? And they're real ISAs. x86 is an example. Spark is another example. These are examples of ISA that use condition codes. And there are good reasons for using condition codes. We're not going to cover them. That's another trade-off in the ISA. Since we don't have time, I don't want to go into that trade-off right now. But assume that this is how it works right now. How do you do branch if 0 in LC3? For example, you calculate a value, and if it's 0, you're going to take one action. You go to one part of the code that does something. If it's not 0, you're going to do something else. That's if then else, right? If this value is 0, do something. If this value is not 0, do something else, right? How do we check that in x86? Basically, there's an sorry, not x86. x86 is actually very similar, but LC3 is this right now. Basically, you have a BRZ instruction, which tests the 0 condition code, and then a PC offset that specifies the destination you go if the 0 condition code is set. Let's take a look at this. And this is the encoding. Basically, you need to set one of these depending on, or one or more of these depending on what condition codes you're testing. So NZP bits, so this is the branch opcode. NZP bits specify which condition code is tested. In this case, Z is tested over here, so these should be 1. the other ones should be 0. And these are the bits to identify the condition codes to be tested. And the larger NZP are the values of the corresponding condition codes in the machine, basically. And PC offset is the immediate or constant value, and we're going to use that to calculate the address. So the semantic specification of the instruction looks like this. If n condition code is being tested and n is set, or p condition code is being tested by the instruction and large P is set, or z condition code is being tested by the instruction and large Z, meaning the Z condition code is set, then set the PC to PC plus sign extended 9-bit offset. So basically, you jump into a location if the condition code that you're testing is set. Make sense? That's the idea. Now you can, it's very powerful. You can test any condition code. You don't need to test 0. You could, if you want to test 0, this is 1 over here. If you want to test n, this is 1 over here, and these are 0. If you want to test whether a condition code is 0 or positive, you set 0, 1, 0 to 1, and p to 1, and n to 0. So you can basically play a lot of tricks depending on what condition you're testing. You can test greater than or equal to 0, less than or equal to 0. You can test equal to 0. You can test greater than 0. You can test less than 0, for example. You can test different condition codes, basically. And the place you jump is a sign extended PC offset added to the program counter. So that's the address of the destination instruction that you're going to jump to. There's a question in chat, actually, that is a nice question. Does this mean we can only jump as wide as 9 bits allow? What about if we want to jump further? That's an excellent question. And the answer is yes. LC3 is a limited ISA. So you can only jump as far as these 9 bits allow, just like any other immediates. That's unfortunate, but that's LC3 for you. If you want to do something bigger, then you need to use something else. In LC3, there's a jump register, for example. You need to do branching, and based on the branching, you execute a jump register instruction. And jump register instruction enables you to specify a value of an entire register and put that into the program counter. So that's an excellent question. So there are other instructions that you have to use. With this instruction, you can only jump so far away from the program counter. So as you can see, there are variations depending on which condition codes you test. So let's take a look at branch C. This is the encoding, basically. And this is how it's executed, basically. They're NZP register. These are condition registers, and you're testing each of them. And the logic is very similar to what I just showed you earlier. So let me actually go back to this logic. This is the Boolean logic. You're testing n condition code and n is set, or you're testing p condition code and p is set, or you're testing z and z is set. Then you set the PC to a different value. So here you can see we're doing that. We're implementing that Boolean logic. And yes means that branch. Basically, set the PC to a destination that's calculated by PC, incremented PC, plus sign extended offset. And PC max basically gets controlled by this yes signal over here. So hopefully this is clear. Now there are some special cases. What if NZ and P are all 1 in your instruction? That means you're testing all of the condition codes. And at least one of the condition codes must be true. This means that this is an unconditional branch. Basically, this is very similar to a jump, except the address is calculated differently. What if you set NZP all to 0 in your instruction? This means that this is not a branch anymore. You're not really testing any condition codes. So the branch is a no operation instruction, basically, because at least one of NZP is true. So let's take a look at conditional branches. MIPS very quickly. MIPS actually has an instruction called branch equal. Basically, it tests if S0 and S1 are equal, and then it basically sets the PC. If S0 and S1 are equal, it sets the PC to PC plus offset. And let's take a look at how it's calculated. Offset is an immediate or constant value. It's 16 bits in MIPS, as you can see. If RS is equal to RT, equality checking, then PC gets PC plus sign extend offset times 4, because instructions are, as you know, word sized, and addresses are byte sized. So we basically multiply the offset by 4 and add it to the incremented PC. So it's very similar addressing mode to what we had in LC3, except the condition checking is very different. We don't have condition codes anymore. We just directly compare the register values. This is branch if equal. And there are other variations of it. And these need to be supported clearly in the MIPS ALU. Branch equal, branch not equal, branch less than or equal, branch greater than 0, for example. There are many other variations. Let's take a look at branch if equal in MIPS and LC3. How is it done? In LC3, if you want to do branch equal, this is what you need to do, basically. I'm going to finish very quickly. After this example will be done. Basically, you can see that since LC3 doesn't allow a branch instruction directly like this, it consumes a lot of operations to subtract R0 from R1. And if the result is 0, then you branch. Essentially, the single instruction is worth 4 instructions in LC3. So you can see again the semantic gap over here. MIPS semantic gap is much lower. So one instruction specifies a lot of work. LC3, you need to do a lot more work. And again, this is an example of the trade-off. The same functionality requires more instructions than LC3, but the control logic is much more complex in MIPS. So go back to the semantic gap slides that we discussed earlier. This is an example of the semantic gap for you. Okay, so this is the end of this lecture. There's a lot more in ISAs, which I'm not going to cover, but if you're really interested, we go into a lot more detail in this older and later course, and there are many different ISAs over decades that you can see, and we cover a lot more trade-offs, but I'm not going to go over these right now. We've covered a lot of these actually, but maybe in the next lecture, we're going to start with a summary of these trade-offs so that I can jog your memory. But next week, we're going to start with microarchitecture, and we're going to go into, well, we've been covering microarchitecture, but we're going to build a microarchitecture from scratch next week so that you can see how it's constructed, as opposed to how you can execute instructions on a microarchitecture someone else constructed. So if there are any burning questions, please feel free to ask. I'm happy to stay, but otherwise, feel free to go and have a very nice weekend. And I will see you next week.
Also es gibt ein Zielbox auf dem so. Das Problem ist, es gibt